when some wag said it's feasible to think responsibly about one thing and not the other. Well, I could see from that one sentence that that was perfectly ridiculous, and it pushed me further into my natural drift, which was into learning all the big ideas and all the big disciplines.
Welcome, curious minds, to the deep dive. Have you ever looked up at the night sky or even just, wondered how your smartphone actually works and felt that deep, inherent human curiosity about how it all comes together?
That drive, yeah.
That drive to understand the fundamental rules of the universe, from the biggest galaxies down to the absolute tiniest particles. Well, that's exactly what physics tries to answer. Some really profound, often mind-bending questions.
Definitely mind-bending sometimes.
Today, we're embarking on a truly monumental deep dive. You, our listener, you've given us this fantastic set of sources, Big Ideas in Physics.pdf. It's a collection really designed to cut through some of the complexity.
Yeah, it's a great starting point.
Our mission, to pull out the most important insights, maybe unearth some truly surprising facts, and connect these huge ideas directly to your everyday life. We want to show you how these theories aren't just for scientists and labs, but they literally govern your existence.
That's exactly right. Physics sometimes gets this reputation for being overly abstract, just full of equations nobody understands.
Right, impenetrable.
Yeah, but really, at its core, it's about understanding the fundamental fabric of reality itself. We'll explore ideas that explain why the universe behaves the way it does, from the smallest, most elusive particles up to the grandest cosmic scales. Our goal today is to go beyond just, defining these concepts.
Yeah.
We really want to provide the so what behind these monumental ideas. What do they actually mean?
I am incredibly excited to unpack this. We're going to journey through, 10 of the most transformative ideas in physics, starting from the classical mechanics that govern, say, a rolling ball,
The basics.
all the way to the frontiers of quantum weirdness and the really ambitious quest for a unified theory of everything. Let's begin. Okay, so we're starting right at the bedrock, the absolute foundation of how anything moves, Sir Isaac Newton's 3 laws of motion. These are, they're the foundation of classical mechanics, which describes pretty much everything you experience day to day.
Almost everything, yeah. At human scales.
Exactly. So the first law, that's the law of inertia. Basically, an object at rest stays at rest, and an object moving in a straight line at a constant speed keeps doing that unless something pushes or pulls on it, an external force. This actually challenges our everyday intuition, doesn't it? We kind of think if you stop pushing something, it'll just stop.
Right. It seems natural for things to slow down.
But Newton clarified, it only stops because something else, like friction or air resistance, is actively pushing back. It needs a force to stop it or change its motion.
A crucial insight.
Then the second law, this is probably the most famous one, F-mo. Simple equation, profound meaning. The net force on an object equals its mass multiplied by its acceleration. It tells you exactly how much an object's motion changes when you apply a force.
It quantifies the relationship. Force, mass, acceleration, all linked.
And finally, the third law. For every action, every force on an object, there's an equal and opposite reaction force. This is so important because it highlights that forces always come in pairs. You can't push on a wall without the wall pushing back on you, right?
Exactly. Interactions. That's the key. It's truly difficult to overstate how revolutionary these laws were back when Newton published them. We're talking 1687 in his huge work, the Principia Mathematica.
A landmark publication.
Absolutely. Before Newton, the thinking, mostly from Aristotle, was that motion needed a continuous push. Stop pushing, it stops moving. That was the idea.
Seems intuitive, I guess.
It does, but it's wrong. Newton, he built upon earlier ideas from people like Galileo, who was already getting a handle on inertia, but Newton's genius was really in unifying these concepts. He created this coherent, universal system. And the key word is universal. It explained the behavior of all objects, from a simple apple falling from a tree right here on Earth.
The famous apple.
The famous apple, right, to the planets orbiting the sun way out there. Imagine that intellectual shift. Suddenly, the same simple rules described why a rock falls and why the moon orbits.
That's incredible, tying it all together.
It showed that if a ball stops rolling, it's not because it naturally wants to stop, but because a force, like friction, is actively slowing it down. This connection between earthly physics and celestial mechanics That was groundbreaking. Nobody had done that before.
And that power is just perfectly captured in FMA. It tells you exactly what happens. You apply a force measured in newtons to an object with a certain mass in kilograms, and you get a specific acceleration in meters per second squared. So like 1 Newton on 1 kilogram gives 1 meter per second squared acceleration. Simple.
Elegant, yeah.
And what's often surprising, I think, is that the first law, inertia, it's actually just a special case of the second law, isn't it?
That's right. If the net force F is 0 in FNA, then the acceleration A has to be 0.
Meaning no change in velocity, it just keeps doing what it was doing.
Exactly. Stays at rest or keeps moving steadily.
And the third law, action-reaction, we can write it simply as F sub A sub. The force of A on B is equal in size, but opposite in direction to the force of B on A.
The mathematical representation of the interaction pair.
But here's where it gets really amazing. Newton didn't just stop there. He actually used his second law, FMA, combined with his other huge idea, the law of universal gravitation.
That's the theory of gravity, yeah.
And he mathematically derived Kepler's laws of planetary motion from those principles. Kepler had described how planets move, but Newton explained why.
That was a stunning moment in science, providing a unified explanation for why the apple falls and why planets trace their elliptical paths. It truly tied the heavens and earth together under one elegant set of rules. Just masterful.
So these laws, they're not just historical footnotes.
Oh, absolutely not. They are the cornerstone of classical physics. Their applications are incredibly diverse and remain indispensable today. Think about engineering.
Right. Bridges, buildings.
Exactly. Designing vehicles, bridges, buildings, engineers are constantly using FU to calculate the forces involved. Acceleration, braking, structural loads, all of it. And rocket propulsion. It's a perfect example of Newton's third law in action. The rocket pushes exhaust gases backward with tremendous force, and the gases push the rocket forward with an equal and opposite force.
Yeah.
Reaction. That's what lifts it off the ground.
Simple principle, incredible results.
Even in sports, you see all three laws constantly. Think about a baseball bat hitting a ball. The ball initially resists changing its motion. That's inertia, the first law.
Okay.
The bat applies a force, F, and the ball accelerates, A, according to F, the second law.
Makes sense.
And at the moment of impact, the ball exerts an equal and opposite force back on the bat. That's the third law, the recoil you feel.
All three in one swing.
Yep. And these laws are incredibly reliable for, most everyday conditions. It's really only when you get into extreme regimes, things moving close to the speed of light or down at the subatomic level, that they start to break down. And you need Einstein's relativity or quantum mechanics.
So for almost everything we experience directly.
For almost everything. Yeah, Newton's laws are profoundly accurate and predictive. They work.
So what does this all mean for you listening right now? These seemingly simple laws explain why you might fall off a skateboard if you hit a rock and suddenly your body wants to keep moving forward because of inertia, even if the board stops beneath you.
Right, that tendency to keep going.
They explain why cars have seat belts. Those belts are designed to apply a force to you to overcome your forward momentum when the car stops quickly.
A safety feature based directly on the first law.
And they literally explain how a rocket leaves Earth's gravity based on that action-reaction principle. From the slightest nudge to the most powerful launch, Newton's laws govern every single push, pull, and movement you experience, right down to the motion of your own body walking down the street. They are truly fundamental.
Couldn't have said it better. They really are the starting point for understanding motion.
Okay, so building on that bedrock of motion, let's talk about something arguably even more fundamental. Conservation laws. You can think of these as like the universe's ultimate accounting principles.
That's a great analogy.
They state that certain physical quantities remain absolutely constant within an isolated system. No matter what happens inside, the total amount of this stuff stays the same. These aren't just guidelines, they're deep statements about what doesn't change.
Unchanging quantities, yeah.
And we're talking about three big ones in classical physics: energy, momentum, and mass. Energy conservation, this one's probably the most famous. It means the total energy of an isolated system never changes. It just transforms from one form to another. Chemical energy in fuel becomes heat and kinetic energy in a call.
Potential energy becomes kinetic as something falls.
Exactly. But the grand total remains constant. That classic saying, energy can neither be created nor destroyed, that sums it up perfectly.
The first law of thermodynamics, basically.
Right. Then there's momentum conservation. If you have an isolated system, the total momentum, which is mass times velocity, remember, remains constant. This is super important in understanding collisions, like billiard balls hitting each other.
The total oomph of this system stays the same.
Kind of, yeah. And finally, mass conservation. In classical physics, anyway, the total mass remains constant in ordinary processes. Matter isn't created or destroyed, it just gets rearranged, like in a chemical reaction.
Atoms just shuffle around.
Exactly. And the real power of these laws is immense. They let us solve problems by just comparing the beginning state and the end state, looking at these conserved quantities without needing to know every single tiny detail of the interactions that happen in between.
It's a shortcut, a very powerful one. Avoids getting bogged down in the dynamics sometimes.
Yeah. So where did these ideas come from? Were they also Newton?
Well, momentum conservation, yeah, that's pretty much implicit in Newton's work. His third law, action-reaction. If two objects interact, any momentum lost by one is gained by the other. So if there are no external forces acting on the system of those two objects, their total momentum stays constant.
Ah, okay. So it followed from his laws of motion.
Pretty directly, yes.
Yeah.
Energy conservation, though, that really took shape in the 19th century. Scientists like James Prescott Joule did these incredibly careful experiments showing that mechanical work and heat were just different forms of the same thing, energy, and could be converted into each other quantitatively.
Mechanical equivalent of heat.
Exactly. Then others, like Julius Mayer and Hermann Helmholtz, generalized the principle, saying all forms of energy, mechanical, thermal, chemical, electrical, could convert, but the total amount was always conserved.
Okay, so that was more of a 19th century development.
Right. And mass conservation? Well, we owe a huge debt to Antoine Lavoisier back in the late 1700s. He was meticulous. He established this principle in chemical reactions by carefully weighing everything before and after the reaction in sealed containers.
Proving mass wasn't lost or gained.
Precisely. He famously stated, mass is neither created nor destroyed in a chemical reaction. Debunked older theories like phlogiston.
Okay, but then things got even deeper, right?
Yes. Here's where it gets really interesting and, frankly, beautiful. In 1918, the brilliant mathematician Emmy Noether proved something truly profound.
Noether's theorem.
Noether's theorem, exactly. She showed that every single conservation law corresponds directly to a fundamental symmetry of nature, a continuous symmetry.
Okay, unpack that. Symmetry.
So, for example, if the laws of physics don't change over time, if they're the same today as they were yesterday and will be tomorrow, that's called time translation symmetry. Noether proves this symmetry mathematically implies the conservation of energy.
Wow, okay.
And if the laws of physics are the same everywhere in space, the same here as on Mars, or in another galaxy, that's space translation symmetry. And that symmetry implies the conservation of momentum.
So the laws being the same leads to these conserved quantities.
Exactly. Noether's theorem explained why these quantities are conserved. It wasn't just something we observed. It was a fundamental consequence of the symmetries underlying the laws of physics themselves. It elevated these conservation laws from just empirical rules to deep properties of the universe's structure. It's an absolutely stunning piece of mathematical physics.
That really does change how you think about them, not just rules, but consequences of symmetry.
Okay, so let's look at the math side a bit, conceptually. For energy, you mentioned a pendulum. Right. At the top of its swing, it's momentarily stationary, so its kinetic energy, energy in motion, is zero. But its potential energy, stored energy due to height, is maximum.
Okay.
As it swings down, it loses height, so potential energy decreases, but it gains speed, so kinetic energy increases. At the bottom, potential is minimum, kinetic is maximum.
And if you ignore friction and air resistance,
The sum of potential and kinetic energy stays exactly constant throughout the swing. Energy just changes form, but the total E is zero for that isolated system.
got it. And for momentum, you mentioned billiard balls.
Classic example. Before the collision, you sum up the momentum, mass times velocity, of both balls.
Yeah.
After they collide and bounce off, you sum up their new momenta. If no external forces acted, like friction from the table, the total momentum before the collision equals the total momentum after. Momentum is just exchanged between the balls,
Yeah.
conditionally at a Treff symbol.
Makes sense. It's conserved in the collision. What about mass? Classically, you said it's just conserved.
Right. Classically, if you react 5 grams of chemical A with 10 grams of chemical B in a sealed flask, you'll end up with exactly 15 grams of products, M total, before M total after. Lavoisier's bread and butter.
But you hinted there's a nuance here.
Ah, yes.
Yeah.
The modern physics view, Einstein's relativity, specifically E avoids MCRA, revealed something profound. Mass and energy are, in a way, two sides of the same coin.
The famous equation.
Indeed. It means a tiny amount of mass can be converted into a huge amount of energy, and vice versa. This happens in nuclear reactions, fusion in the sun, fission in power plants. A small amount of mass is lost and released as energy.
So mass isn't strictly conserved in those cases?
Not on its own, but mass energy as a combined quantity is conserved, so the total amount of mass plus energy remains constant. However, for everyday chemical reactions or mechanical processes, the energy changes are so small that the corresponding mass changes from E phase area are absolutely minuscule, practically undetectable.
So for everyday purposes, we can still treat mass as conserved.
Absolutely. In chemistry, engineering, everyday life, mass conservation holds extremely well. But fundamentally, it's mass energy that's the truly conserved quantity.
Okay, that's a crucial distinction. So where do we see these laws applied?
Everywhere. Mechanical systems, like roller coasters engineers, use energy conservation constantly. Potential energy at the top becomes kinetic energy at the bottom, minus some losses to friction, of course.
Collision analysis.
Definitely. Accident reconstruction uses momentum conservation to figure out speeds before impact based on what happened after. Rocket science, as we mentioned, relies heavily on momentum conservation. Expelling mass backwards gives the rocket forward momentum.
Thermodynamics.
Energy conservation is literally the first law of thermodynamics. It ensures all energy is accounted for in engines, power plants, refrigerators. Input energy equals output work plus waste heat. Nothing is free.
Chemistry, you mentioned Lavoisier.
Fundamental for stoichiometry, balancing equations, predicting yields. Environmental science, too, tracking pollutants, often relies on mass balance calculations.
And they set limits, right?
Absolutely. Philosophically, they set fundamental constraints. Perpetual motion machines that violate energy conservation. Impossible. You can't get something from nothing.
And they guide discoveries.
Yes. A famous example is the neutrino. In the early 20th century, physicists observed a type of radioactive decay called beta decay, and it looked like energy and momentum weren't conserved.
Uh-oh.
Instead of abandoning these fundamental principles, Wolfgang Pauli boldly proposed that an unseen, undetected particle must be carrying away the missing energy and momentum.
The neutrino.
Exactly. It was experimentally confirmed decades later. So the belief in conservation laws actually led to the prediction and discovery of a new fundamental particle. They are incredibly powerful tools, ingrained in every field of physics, telling us what can't happen as much as what can.
Think about it. These laws are why you can't make an engine that's 100% efficient. You always lose some energy as heat. You can't just destroy it. They're why a ball thrown up always comes back down, assuming you don't throw it too hard, converting kinetic energy to potential and back again. They are, like you said, the universe's ultimate accountants, just meticulously tracking the fundamental stuff of reality, ensuring it's all preserved, even as it changes form.
Perfectly put. They provide a deep sense of order amidst all the change.
Okay, from the universe's accounting principles, let's talk about something equally profound. The universe's intrinsic direction, the flow of processes, which brings us to thermodynamics and the crucial concept of entropy.
Ah, yes, the arrow of time.
Exactly. Thermodynamics is the study of heat, energy, and work. It describes not just how energy moves and transforms, but crucially, why certain processes happen spontaneously and others don't, why things seem to have a preferred direction in time.
Irreversibility.
Yeah. So the first law of thermodynamics, as you mentioned, is basically energy conservation applied to heat and work. Any heat added to a system either increases its internal energy, makes it hotter, or gets used by the system to do work, like expanding against a piston. VO-cube is QW energy is accounted for.
Straightforward conservation.
But the real star, the one with the deep implications, is the second law. This introduces entropy, which is often described as a measure of disorder, but maybe more accurately, it's about the dispersal or spreading out of energy.
How energy spreads out, yeah. Quality degrades, in a sense.
Right. The second law states that the total entropy of an isolated system always tends to increase over time, or at best, stay constant in perfectly ideal reversible processes. But in any real-world process, entropy goes up. What does that mean practically? It means energy naturally spreads out from being concentrated to being dispersed. Heat flows spontaneously from hot to cold, never the other way around. Things tend to go from ordered states to disordered states.
Like a broken glass never spontaneously reassembles itself.
Exactly. That's why we often call entropy the arrow of time. It points the direction in which natural processes occur, overwhelmingly moving towards states of higher entropy, greater disorder, or dispersal.
It gives time its directionality, which is missing from Newton's laws, for example.
And briefly, the third law. As a system's temperature approaches absolute zero Kelvin, about -273 Celsius, its entropy approaches a minimum constant value, often taken as zero for perfect crystals. This also implies that reaching absolute zero is physically impossible in a finite number of steps.
You can get incredibly close, but never quite there.
So these laws together describe how energy moves, transforms, and why some processes are just, well, one-way streets.
Thermodynamics really came into its own during the 19th century. It was heavily driven by the Industrial Revolution, the need to understand and improve steam engines.
Practical needs driving fundamental science.
Absolutely. Early pioneers like Sadi Carnot, back in the 1820s, started analyzing engine efficiency, realizing the importance of temperature differences. But it was Rudolf Clausius and William Thomson, Lord Kelvin, who really formulated the first and second laws clearly in the 1850s. Clausius actually coined the term entropy in 1865, and he had this incredibly concise and profound summary of the first two laws. The energy of the universe is constant. The entropy of the universe tends to a maximum.
Wow. That packs a punch. Energy conserved, disorder increasing.
It really does. Then came Ludwig Boltzmann in the 1870s. He provided a revolutionary statistical interpretation of entropy. He connected it directly to the number of possible microscopic arrangements, microstates, that correspond to the system's overall macroscopic state.
Right.
S equals KDLNA.
So he linked the big picture, thermodynamics, to the small picture, atoms.
Precisely. It bridged thermodynamics and atomic theory. His insight was that entropy increases simply because there are vastly more ways for particles to be arranged in a disordered state than in an ordered state. Disorder is just much more probable.
So it's about probability.
Overwhelmingly so. This statistical view helped explain why entropy gives time a direction, even though the underlying laws governing particle collisions might be reversible. It also led to concepts like the absolute temperature scale, Kelvin, and free energy, which is crucial for predicting chemical reactions.
And you mentioned the fate of the universe.
Yeah, the second law has these deep philosophical implications.
Yeah.
If the entropy of the universe is always increasing, it points towards a potential end state, the heat death, where all energy is uniformly spread out, temperatures are equal everywhere, and no more useful work can be done. Everything just sort of stops. Rather grim forecast, perhaps.
Okay, let's quickly touch on the math again. The first law, U, Dorges, QW. So if you add, say, 200 joules of heat to a gas, and the gas does 50 joules of work, W, by expanding, its internal energy increases by 150 joules. Simple energy balance.
Okay.
The second law is often expressed as IO 0 for a closed system. Entropy increases 0 for any real irreversible process and only stays constant for hypothetical perfectly reversible ones.
And there are those famous statements, like Clausius's. Heat doesn't spontaneously flow from cold to hot, or Kelvin Planck's. You can't build an engine that just takes heat from a single reservoir and converts it all into work without dumping some waste heat somewhere colder.
Right, no perfect efficiency. Which relates to Boltzmann's S equals KBLNA disorder, more possible microstates, AA, is simply statistically favored. Like mixing gases, the mixed state has vastly more possible arrangements than the separated state.
Exactly. The system naturally evolves toward the state with the highest number of possibilities, the highest entropy.
And the third law, as temperature T approaches 0 Kelvin, entropy S approaches a constant minimum, usually 0.
Setting a baseline and implying absolute zero is unattainable.
So the impact of all this irreversibility seems huge.
It is. It explains why you can't unscramble an egg, or why smoke doesn't spontaneously go back into a chimney, or why coffee and cream mix but don't unmix on their own. These processes naturally move toward higher entropy states.
And the arrow of time.
It's deeply connected. We experience time flowing in one direction because macroscopic processes are overwhelmingly irreversible due to entropy increase. We remember the past, generally lower entropy, but not the future, higher entropy. Systems evolve towards equilibrium, which is the state of maximum entropy for that system.
What about engineering? You mentioned limits.
Absolutely critical. The second law dictates the maximum possible efficiency of any heat engine. The famous Carnot efficiency, E-Romex 1 T sub cold sub hot sub, shows that efficiency depends on the temperature difference between the hot source and the cold exhaust. Since sub-cold sub can't be absolute zero, no engine can ever be 100% efficient.
So some waste heat is unavoidable.
Always. This applies to power plants, car engines, refrigerators, everything that moves heat around. In chemistry, Gibbs' free energy, GSHTS, which incorporates entropy, tells chemists whether a reaction will happen spontaneously under given conditions.
Any surprising connections?
Well, maybe the link to information theory. Claude Shannon realized that the mathematical form of entropy also measures uncertainty or information content in data. So the concept has reached beyond just physics.
And cosmology.
Oh, yes. The universe as a whole seems to obey the second law. Its total entropy has been increasing since the very low entropy state of the Big Bang, heading towards a more disordered future. Even processes that seem to create order locally, like star formation, do so at the cost of increasing the entropy of their surroundings even more.
So Clausius's statement really holds true on the grandest scale.
It seems so. The energy of the universe is constant. The entropy of the universe tends to a maximum. It's a profound summary of cosmic destiny as we currently understand it.
So this is the why behind so many everyday things we just take for granted. Why ice melts in a warm room, why your hot coffee inevitably gets cold, why your room tends to get messy and never spontaneously tidies itself.
Unless you expend energy to tidy it, increasing entropy elsewhere.
Right, it's like the universal law of things fall apart or maybe things spread out, but it happens in this highly predictable, quantifiable way. And it gives the universe a direction, this arrow of time, shaping everything from a simple chemical reaction to, potentially, the ultimate fate of the entire cosmos. It's a really deep concept.
One of the deepest in all of physics, I'd argue.
All right, from the flow of time and energy dispersal, let's pivot to something that powers our modern world. Electromagnetism. This is the amazing theory that brought together electricity and magnetism, showing they weren't separate phenomena, but two aspects of a single unified force. And it's all captured, incredibly elegantly, in just 4 equations by James Clerk Maxwell.
A monumental achievement. Right up there with Newton.
So let's briefly touch on what these equations tell us, roughly. Gauss's law for electricity says electric charges create electric fields that point outward or inward. Gauss's law for magnetism essentially says there are no magnetic monopoles. Magnetic field lines always form closed loops, like around a bar magnet. You always have a north and a south pole.
No magnetic charges equivalent to electric charges.
Exactly. Then Faraday's law of induction, this is huge. It says a changing magnetic field produces an electric field. This is the principle behind electric generators.
Crucial for power generation.
And finally, the Ampere-Maxwell law. This says magnetic fields are produced by electric currents, and this was Maxwell's key addition also by changing electric fields. That last bit, the displacement current, was the missing piece that made the whole theory consistent and complete.
The stroke of genius that unlocked everything else.
And the most stunning implication of pulling all this together. Maxwell's unification mathematically predicted that disturbances in these electric and magnetic fields would travel as waves, and the speed of these waves
Matched the speed of light.
exactly, which led Maxwell to the incredible conclusion that light itself is an electromagnetic wave, just a self-propagating ripple of oscillating electric and magnetic fields. It wasn't just unifying electricity and magnetism, it unified them with optics, the science of light.
It was truly one of the greatest unifications in the history of physics. Before Maxwell, people like Ørsted had shown electric currents affect magnets, and Faraday had shown moving magnets induce currents, so hints were there.
Connecting the dots.
Right. But it was James Clerk Maxwell in the 1860s who synthesized all these known laws into one coherent mathematical framework. The absolutely brilliant part was his hypothesis of that displacement current. The idea that a changing electric field could also create a magnetic field, just like a current does. Without that term, the equations didn't quite work, especially in empty space.
So he added it based on theoretical consistency.
He did, partly for symmetry and consistency, and in 1865 he published his full set of equations. And that's when the magic happened. He showed these equations predicted waves propagating at a very specific speed. He calculated this speed using known electrical and magnetic constants.
Constants you could measure in a lab.
Exactly. And the number he got was astonishingly close to the experimentally measured speed of light. So he made the bold leap. Light is an electromagnetic wave.
What a moment that must have been.
Imagine. It was this stunning synthesis. Like Newton unifying falling apples and orbiting planets, Maxwell unified electricity, magnetism, and light into a single phenomenon. And it wasn't just theory for long. Heinrich Hertz, in 1888, experimentally generated and detected radio waves, confirming Maxwell's electromagnetic waves existed beyond visible light.
Proving him right.
Absolutely.
Right.
It's also worth noting the concise 4 equations we usually see today were actually condensed later by Oliver Heaviside from Maxwell's original, more complex formulation. But the physics is all Maxwell's.
So mathematically, even conceptually, these 4 equations are packed with meaning. Gauss's law for electricity. Field lines depend on charges. Gauss for magnetism. Magnetic field lines loop, no endpoints. Faraday's law. Changing a magnetic flux creates circulating electric fields, how generators work. And Ampere-Maxwell. Currents and changing electric fields create circulating magnetic fields.
That last one is key for waves. A changing E field makes a B field. which changes, making an E-field and so on.
allowing the wave to propagate itself through space.
Yeah.
And the math showed this happens at a speed cc equals 1 sheet Marrow, where rho and errs are fundamental constants of electricity and magnetism. When Maxwell plugged in the values,
Bingo. Speed of light.
the equations also describe the nature of these waves. The electric and magnetic fields oscillate perpendicular to each other and also perpendicular to the direction the wave is traveling.
Transverse waves.
Right. And here's another crucial connection we touched on. Maxwell's equations predicting this constant speed of light c were actually incompatible with older ideas about adding velocities. This apparent contradiction was a major puzzle that directly motivated Einstein to develop special relativity.
Maxwell inadvertently set the stage for Einstein's revolution. Yeah. His equations already had relativity sort of built into them even before Einstein figured it all out.
The impact of electromagnetism is just staggering.
It's almost impossible to list everything. You can state it simply, virtually all modern electrical and communications technology stems directly from Maxwell's theory.
Okay, like what?
Communications, radio, television, Wi-Fi, cell phones, satellites, all rely on transmitting and receiving electromagnetic waves. Power. Electric generators use Faraday's law. Transformers use it to change voltages for efficient distribution over power lines. Devices. Electric motors convert electrical energy to motion using magnetic fields. Generators do the reverse.
Light itself.
Lasers, fiber optics, all our understanding of light as an EM wave. Everyday tech. Microwave ovens use microwaves, EM waves, to heat food. MRI machines use radio waves and magnetic fields for medical imaging. Even the basic circuitry in your computer or smartphone manipulating electrical signals relies on these principles.
And scientifically.
Huge impact. Maxwell's work revealed the entire electromagnetic spectrum beyond visible light radio waves, infrared, ultraviolet, X-rays, gamma rays. This completely revolutionized astronomy. We can now observe the universe across all these wavelengths, seeing things invisible to optical telescopes like the cosmic microwave background itself.
A whole new view of the cosmos.
And conceptually, Maxwell introduced the field concept, the idea that forces are mediated by fields filling space. This became a central idea in all of modern physics, paving the way for quantum field theory. It's undeniably one of the greatest triumphs of physics, elegantly fusing electricity, magnetism, and optics into one powerful framework. It also serves as a template for later theories, like the gauge symmetries used in the Standard Model.
So when you think about it, the light's on in your room right now, the wireless signal bringing this conversation to you, the colors you see, the electricity powering your device, it's all just this intricate, invisible dance of electric and magnetic fields, all described by Maxwell's equations from over 150 years ago. This single theory literally powers and illuminates our entire modern world.
It really does. Hard to imagine life without it.
Okay, we've covered some huge ground with classical mechanics, thermodynamics, and electromagnetism. But now we're stepping into the 20th century and the theories that truly revolutionized our understanding of reality itself. First up, Einstein's theories of relativity. This is where familiar notions of space, time, and gravity get completely turned on their heads.
A true paradigm shift, or maybe two shifts.
Right. First, there's special relativity, which Einstein published in 1905. This deals with physics in the absence of gravity, and it's built on two surprisingly simple postulates. One, the laws of physics are the same for all observers who are moving at a constant velocity. So, no preferred frame of reference.
The principle of relativity, yeah, extending Galileo's idea.
And two, the really radical one. The speed of light in a vacuum is constant for all observers, regardless of their own motion or the motion of the light source, about 300 million meters per second, always.
That second postulate is the kicker. It has profound consequences.
Absolutely. From just those two ideas, Einstein derives some truly bizarre effects. Time dilation, meaning moving clocks actually tick slower relative to stationary ones. Length contraction moving objects appear shorter in their direction of motion. And, of course, the most famous equation in physics, E equals mc os, revealing the astonishing equivalence of mass and energy. Mass is a form of energy, and energy has mass.
Mind-bending consequences from simple starting points.
Then, 10 years later, in 1915, Einstein unveiled general relativity. This extended his theory to include gravity, and his insight here was revolutionary. Gravity is not a force pulling objects together, as Newton thought. Instead, gravity is the curvature of space-time caused by the presence of mass and energy.
Space-time itself is warped.
Exactly. The common analogy is placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip, a curvature. If you roll a marble nearby, it doesn't get pulled by the ball. It simply follows the curve in the sheet caused by the ball.
So massive objects warp space-time around them.
And other objects, or even light, follow the curves in that warped space-time. That's what we perceive as gravity. The famous summary is, matter tells space-time how to curve, and space-time tells matter how to move.
Elegance.
And general relativity made a whole host of new verifiable predictions. Gravitational time dilation clocks tick slower not just when moving fast, but also when they're deeper in a gravitational field. The bending of light by gravity. Tiny deviations in planetary orbits like Mercury's. And more exotically, the possibility of black holes and the existence of gravitational waves ripples in the fabric of space-time itself.
It was a complete rethinking of gravity, space, and time. The context here is key. In the late 19th century, there was this nagging conflict. Newtonian mechanics said velocities just add up simply. If you're on a train moving at 50 mph and throw the ball forward at 10 mph, someone on the ground sees it moving at 60 mph.
Makes sense.
But Maxwell's equations for electromagnetism implied that the speed of light, cs, was a constant fixed value. It didn't depend on the speed of the source or the observer. This seemed contradictory. The Michelson-Morley experiment in 1887 famously tried to detect Earth's motion through a supposed ether that light waves traveled in, but found no difference in light speed, reinforcing its constancy.
So experiments supported Maxwell.
They did, and Einstein, in 1905, took the bold step. Instead of trying to force light to fit Newtonian ideas, he took the constant speed of light as a fundamental principle. He realized that if c is constant for everyone, that our notions of absolute space and absolute time must be wrong.
They have to adjust to keep c constant.
Exactly. Space and time become relative, interwoven. Measurements of length and duration depend on the observer's motion. That led directly to special relativity, time dilation, length contraction. And shortly after, he derived Eames' de Tissot, showing mass as concentrated energy. This wasn't just theory. Experiments soon confirmed it, like observing fast-moving subatomic particles living longer than expected due to time dilation.
And then came general relativity.
Right. Einstein spent the next decade wrestling with how to incorporate gravity. He was guided by his equivalence principle, the insight that, locally, the effects of gravity are indistinguishable from the effects of acceleration. Like being in an accelerating elevator feels just like gravity.
Okay.
This led him to the idea that gravity must be related to the geometry of space-time. In 1915, he finally published the field equations of general relativity, describing precisely how mass and energy curve space-time. This new theory matched Newton's gravity in everyday situations, but made distinct predictions in strong gravitational fields or for light.
And the big confirmation.
The dramatic confirmation came in 1919. Sir Arthur Eddington led expeditions to observe a solar eclipse. They measured the position of stars near the sun, whose light had to pass through the sun's gravitational field. General relativity predicted the light would be bent by a specific amount due to the sun's warping of space-time, twice the amount predicted by Newtonian gravity if you treated light as having mass. Eddington's measurements matched Einstein's prediction perfectly. It was front-page news worldwide, made Einstein an international icon overnight.
Wow.
And since then, GR have been vindicated again and again. It explained the weird precession of Mercury's orbit perfectly. Gravitational time dilation has been measured with atomic clocks. And the most spectacular confirmation came in 2015, when the LIGO experiment directly detected gravitational waves from two merging black holes, ripples in space-time, exactly as Einstein predicted a century earlier.
100 years later. That's incredible. Okay, let's talk math concepts. In special relativity, you mentioned the gamma factor. Article 1.1, T sub ohm to V cellular, this pops up everywhere.
It's the key factor that determines how much time dilates and length contracts. It depends only on your velocity v relative to the speed of light c.
And as it gets closer to c, gamma gets larger and larger, approaching infinity at the speed of light.
Right, which means time dilation becomes infinite. Time stops, in a sense. And length contraction shrinks lengths to zero. It also means the energy required to accelerate an object with mass to light speed becomes infinite. That's why massive objects can't reach c.
A universal speed limit built right in. And EMC Merkel, where does that come from?
It emerges naturally from requiring energy and momentum conservation to hold true within the framework of special relativity. It fundamentally shows that mass itself is a form of energy, even when an object is at rest. Rest energy is MC Merkel. And when moving, its total energy is E equals Gonsi-Arauco. Its confirmation in nuclear reactions, where tiny mass deficits release enormous energy, is undeniable.
And general relativity, the math there seems way more complex.
It is. The core is Einstein's field equation. Conceptually, it's an equation that relates the geometry of spacetime, represented by things called tensors describing curvature on one side, to the distribution of mass and energy, represented by another tensor on the other side. For Subi sub 1 have R Subi sub only about the GCR. Subi sub, don't worry about the symbols.
Okay. Just the concept. Geometry equals mass-energy distribution.
Exactly. You tell the equation how mass and energy are laid out, and it tells you how spacetime curves in response. Solving this equation for specific situations gives specific spacetime geometries. Carl Schwarzschild found the first exact solution just months after Einstein published the theory, describing the spacetime around a spherical mass. That solution predicted black holes, with an event horizon radius or equals 2 GMC-us.
The point of no return.
Precisely. GR also predicts gravitational time dilation, quantitatively clocks deeper and gravity runs slower, and it predicts the exact angle light should bend when passing a massive object. The core idea is just so elegant. Objects follow the straightest possible paths, geodesics, in this curved space-time. What we call gravitational acceleration is just objects following the dictates of the geometry.
Okay, this isn't just abstract theory. You mentioned GPS.
The most famous practical application. GPS satellites orbit high above Earth and move very fast. Special relativity says their clocks should run slower than clocks on Earth because they're moving fast. General relativity says their clocks should run faster because they're in weaker gravity than we are on the surface.
So two competing effects.
Yes, and the GR effect is actually larger. The net result is that satellite clocks run faster than ground clocks by about 38 microseconds per day. It sounds tiny, but GPS relies on nanosecond timing accuracy. If you didn't account for both relativistic effects, the system would accumulate errors of several kilometers per day and be totally useless for navigation.
Wow. So my phone's map relies directly on Einstein.
Absolutely. Every time you use GPS.
Yep.
Beyond that, particle accelerators like the LHC rely heavily on SR. Protons are accelerated to 99.999% the speed of light. Time dilation dramatically increases their observed lifetimes, and their effective mass increases enormously, which engineers have to account for. Huge implications. It explains nuclear fusion powering the sun and stars. It's a basis for nuclear energy generation and, unfortunately, nuclear weapons.
And cosmology.
GR is the essential framework for understanding the universe at large scales. It predicts the expansion of the universe, providing the foundation for the Big Bang theory, which is now overwhelmingly supported by evidence like the CMB.
Holes.
The study of black holes is entirely dependent on GR. Interpreting observations like X-rays from accretion disks, the orbits of stars around the supermassive black hole at our galaxy center, and even that incredible image of the M87 black hole shadow all require GR.
Gravitational lensing.
Another direct prediction. Massive objects bending light acts like a lens. Astronomers use it routinely to study distant galaxies, map dark matter distribution, and even detect exoplanets.
And gravitational waves.
The direct detection by LIGO in 2015 opened a completely new way to see the universe gravitational wave astronomy. We can now observe incredibly violent events like merging black holes and neutron stars that are invisible to light-based telescopes.
So the conceptual shift was massive, too.
Absolutely. Einstein demolished the idea of absolute space and absolute time. He showed they're interwoven into a dynamic space-time fabric that can stretch, shrink, and ripple. It clarified causality. Nothing with mass can travel faster than light, setting a cosmic speed limit. The equivalence of mass and energy changed our fundamental understanding of matter. GR showed the universe isn't a static stage, but a dynamic, evolving arena, as Hermann Minkowski put it so well back in 1908. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality.
That really captures it.
So relativity reshaped our worldview from the practicalities of GPS to the grand scale of cosmology, affecting our understanding of everything from energy to the structure of reality itself.
It's truly wild to think that your phone's GPS navigation relies on Einstein's incredibly abstract and mind-bending theories about how speed and gravity literally distort time and space. Relativity isn't just for describing black holes or the Big Bang. It's woven into the fabric of our modern technological life, forcing us to revise our deepest intuitions about the very nature of reality.
A true revolution in thought.
All right, if relativity stretched our minds dealing with the very large and very fast, quantum mechanics takes us to the realm of the incredibly small atoms and subatomic particles, and things get even weirder. This is the theory describing matter and energy at those tiny scales, where all the classical rules we've discussed just completely fall apart.
If you thought relativity was weird, buckle up.
Right. So what are the core ideas? First, wave-particle duality. This is maybe the cornerstone. It says that things we usually think of as particles, like electrons, can behave like waves under certain conditions. And things we think of as waves, like light, can behave like particles called photons. It depends entirely on how you set up your experiment to observe them.
They have aspects of both. Very counterintuitive.
Then there's quantization. This means many properties, like energy, especially for bound systems like electrons and atoms, don't come in a smooth continuum of values. They only exist in discrete, specific amounts or packets called quanta. Think of it like energy levels being specific rungs on a ladder, not a continuous ramp. Electrons can only be on the rungs, not in between.
Energy comes in chunks at the micro level.
Next up, the famous uncertainty principle, formulated by Werner Heisenberg. This states that you fundamentally cannot know certain pairs of properties of a particle, like its precise position and its precise momentum, mass times velocity, simultaneously with perfect accuracy. The more precisely you know one, the less precisely you can possibly know the other.
And crucially, this isn't a limitation of our measurement tools. It's an inherent property of nature itself, a fundamental fuzziness.
Right. Then there's superposition. This means a quantum system can exist in a combination of multiple possible states at the same time until you actually measure it. The classic, if morbid illustration, is Schrödinger's cat paradox. The hypothetical cat inside a box, linked to a quantum event, is considered both alive and dead simultaneously until the box is opened and a measurement is made.
It exists in a probabilistic limbo until observed.
And finally, entanglement. This is what Einstein famously called spooky action at a distance. Two or more quantum particles can become linked in such a way that they share the same fate, no matter how far apart they are separated. Measuring a property of one particle instantaneously influences the possible outcomes for the other. Their fates are intertwined.
A deep non-local connection.
So, in quantum mechanics, instead of definite trajectories, we talk about the wave function, represented by A, yes. This mathematical object describes the state of a quantum system, but it encodes probabilities for the outcomes of measurements. When you actually make a measurement, the wave function is said to collapse, and you get one definite result out of the possibilities. It's inherently probabilistic.
Determinism goes out the window, replaced by probabilities. That was a huge philosophical shift.
Where did all this strangeness come from?
It emerged in the early 20th century because classical physics just failed to explain several key experimental observations at the atomic level. It started around 1900 with Max Planck. He was trying to explain black body radiation, how objects glow when heated. He could only get the theory to match experiments if he assumed that energy was emitted and absorbed in discrete packets, or quanta, proportional to frequency. E was Planck's constant.
So quantization started there.
Yes. Then Einstein, in his miracle year 1905, used Planck's idea to explain the photoelectric effect, how light knocks electrons out of metals. He proposed that light itself is made of these energy packets, later called photons, solidifying the particle nature of light.
Wave-particle duality emerging early.
Exactly. Then Niels Bohr, in 1913, proposed his model of the atom with quantized electron orbits to explain the specific colors of light emitted by atoms, atomic spectra. Electrons could only jump between these specific energy levels, emitting or absorbing photons of specific energies.
Okay, so pieces were falling into place.
But the full mathematical theory really exploded in the mid-1920s. Louis de Broglie proposed in 1924 that if waves can be particles, maybe particles can be waves. This was quickly confirmed by experiments showing electrons diffracting like waves. Then came the giants. Werner Heisenberg developed matrix mechanics. Erwin Schrödinger developed his famous wave equation, which describes how the wave function evolves, and Paul Dirac provided a relativistic unification. Amazingly, these different mathematical approaches were shown to be equivalent.
A frenzy of development.
Absolutely. Max Born provided the crucial interpretation. The square of the wave function's amplitude gives the probability of finding the particle. This introduced the inherent probabilistic nature that troubled so many, including Einstein. Heisenberg formalized the uncertainty principle in 1927.
And Einstein's spooky action.
That came from the EPR paradox paper in 1935, where Einstein, Podolsky, and Rosen highlighted the weirdness of entanglement to argue that quantum mechanics must be incomplete. They thought there must be hidden variables determining the outcomes. But later work by John Bell in the 1960s and crucial experiments by Elaine Aspect and others in the 1980s confirmed quantum mechanics predictions about entanglement. They showed that nature is indeed fundamentally probabilistic and non-local in this spooky way. No hidden variables as Einstein hoped. This really cemented the quantum revolution.
Wow, so the weirdness is real. Mathematically, you mentioned the Schrödinger equation.
Right. It's the fundamental equation of non-relativistic quantum mechanics. Equa. It describes how the wave function evolves in time under the influence of forces, represented by eta Hamiltonian. Solving it for systems like the hydrogen atom correctly predicted the observed energy levels, which was a massive success.
And the Born rule connects the math to reality.
Exactly. It says et x orbitus gives a probability density of finding the particle at position x. This is totally different from classical physics, where a particle has a definite position at all times. Here, you only have probabilities until you measure.
The uncertainty principle also comes from the math.
Yes, it arises fundamentally from the wave nature of particles and the mathematical properties of operators representing position and momentum. They don't commute, meaning the order you apply them matters, which leads directly to the uncertainty relation. It's a fundamental limit, not just about measurement disturbance.
What about that double slit experiment? That seems to capture all the weirdness.
It really is the quintessential quantum experiment. If you fire single electrons one at a time towards a barrier with two slits, you'd classically expect two bands on the screen behind it.
Right, where they went through.
But instead, they build up an interference pattern alternating bright and dark bands, just like waves would. This suggests each electron somehow interfered with itself, as if it went through both slits simultaneously in a superposition.
But if you try to watch which slit it goes through?
Then the interference pattern disappears. The electrons suddenly behave like particles. Going through one slit or the other, you just get two bands. The very act of measuring which path destroys the wave-like superposition and forces a particle-like outcome. Observation changes reality.
Mind-bending.
And superposition allows this.
Yes, before measurement, the electron exists in a superposition state of went through slit A plus went through slit B. Measurement forces it into either state A or state B. Entanglement is similar, but involves multiple particles linked by a single wave function. Measuring one particle instantly collapses the wave function for all entangled particles, determining their correlated properties no matter how far apart. It's weird, but experimentally verified. No faster-than-light communication, though, just correlations.
Okay, despite the weirdness, this theory must be incredibly important.
Oh, absolutely fundamental.
Yeah.
It's the foundation of basically all modern chemistry, material science, and much of today's technology.
Like what?
Chemistry. The entire periodic table, how atoms bond to form molecules, chemical reactions, it's all governed by the quantum behavior of electrons. Electronics. Semiconductor physics, which relies on the quantum band theory of electrons in solids, is the basis for transistors, integrated circuits, computer chips, LEDs, solar cells. Essentially all modern electronics. Direct application of quantum principles like stimulated emission, first described by Einstein way back in 1917. Medicine. MRI, magnetic resonance imaging, depends entirely on the quantum property of nuclear spin. Precision timing. Atomic clocks, the most accurate timekeepers we have, rely on precise quantum transitions in atoms. They're essential for GPS and global time standards.
What else?
Exotic phenomena like superconductivity, zero electrical resistance, and superfluidity are purely quantum effects. Even everyday things like fluorescent lights and modern display screens, like OLEDs, rely on quantum jumps of electrons.
And future tech.
Huge potential. Quantum computing aims to harness superposition and entanglement to perform calculations impossible for classical computers. Quantum cryptography promises fundamentally secure communication based on the uncertainty principle. Quantum sensors could offer unprecedented precision.
And the philosophical impact.
Profound. It shattered classical determinism. We learned that at the fundamental level, reality is probabilistic. It sparked decades of debate about interpretation, what the wave function means, Copenhagen interpretation, many worlds, etc. It forced us to accept that the microworld operates by entirely different counterintuitive rules. As Richard Feynman famously said, I think I can safely say that nobody understands quantum mechanics. Yet, its predictions are among the most precisely tested and verified in all of science. Quantum electrodynamics, for example, makes predictions that match experiments to about 1 part in a billion.
So it's weird, maybe impossible to intuitively grasp, but it works incredibly well.
Exactly. It gave us a much deeper, albeit stranger, understanding of the microworld, and it's undeniably the bedrock of the technologies that define our modern era.
This is where physics gets truly, truly mind-bending. Your smartphone in your pocket, the medical scans that can see inside you, even the light from your screen right now, all of it depends on the utterly bizarre rules of the quantum world, where particles can be waves, exist in multiple states at once, and where the act of observation fundamentally changes the outcome. It's the ultimate aha moment that our classical intuitions about reality are just plain wrong at the most fundamental level. We had to completely revise our picture.
A necessary, if baffling, revision.
Okay, we've journeyed from Newton's laws through the warping of space-time and relativity and the probabilistic weirdness of quantum mechanics. Now we arrive at our current, most successful description of the fundamental particles and forces that make up almost everything we know, the standard model of particle physics.
Our best parts list for the universe, essentially.
Exactly. Think of it as the universe's detailed instruction manual, or maybe its periodic table for the fundamental building blocks. It describes all the known elementary particles and how they interact via 3 of the 4 fundamental forces. It explains everything except gravity.
That's the big missing piece, yeah. Gravity isn't included.
Right. So the standard model neatly classifies particles into 2 main groups. Fermions, which are the matter particles, like electrons and quarks, and bosons, which mediate the forces, like photons.
Matter stuff and force stuff.
Pretty much. The fermions themselves split into 2 families. Quarks, there are 6 flavors of them. Up, down, charm, strange, top, and bottom. Quarks combine in groups to form composite particles like protons, 2 ups and a down quark, and neutrons, 1 up and 2 downs. They're never found alone, always bound together.
Bound by the strong force.
And the other fermion family is the leptons. There are also 6 of these. The familiar electron plus its heavier cousins, the muon and the tau. And each of these has a corresponding, nearly massless, very elusive partner called a neutrino, electron neutrino, muon neutrino, tau neutrino. Unlike quarks, leptons can exist on their own.
Like the electron orbiting an atom.
Exactly. Both quarks and leptons are organized into 3 generations. The first generation, up-down quarks, electron, electron, neutrino, makes up all ordinary matter. The second and third generations are heavier, unstable copies that existed in the early universe and can be created in particle accelerators.
Heavier duplicates, essentially.
Then we have the bosons, the force carriers. The photon carries the electromagnetic force responsible for light, electricity, and magnetism. The WUSUP plus SUP, WUSUP-SUP, and ZSUP-SUP bosons carry the weak nuclear force, which is responsible for certain types of radioactive decay and processes crucial for stars to shine. And finally, 8 gluons carry the strong nuclear force, which glues quarks together inside protons and neutrons, and also binds protons and neutrons together in atomic nuclei.
So photon for EM, WZ for weak, gluons for strong.
Got it. But there's one more crucial piece. The Higgs boson. It's a different kind of boson associated with an energy field, the Higgs field, that permeates all of space. It's the interaction with this field that gives fundamental particles like the W and Z bosons and all the quarks and charged leptons their mass.
The particle responsible for mass. A huge discovery.
So that's the cast of characters in the standard model: 12 fermions, 6 quarks, 6 leptons, arranged in 3 generations, 4 types of force carriers, photon, WZ, gluons, plus the Higgs boson. It's a quantum field theory built on quantum mechanics and special relativity and based on fundamental symmetries. The image provided in the source shows this structure nicely.
It's an incredibly elegant and predictive framework, but it definitely didn't just appear overnight. It was built piece by piece over decades of experimental discoveries and theoretical breakthroughs.
A real collaborative effort.
Absolutely. It started with discovering the electron in 1897, then the nucleus. But the real explosion came in the mid-20th century with particle accelerators. Suddenly, physicists were discovering dozens of new particles, a confusing particle zoo.
You needed organizing.
Exactly. A major breakthrough came in 1964 when Murray Gell-Mann and George Zweig independently proposed the quark model, suggesting that many of these zoo particles, like protons and neutrons, were actually made of smaller, more fundamental things called quarks. This was seen as a bit radical at first.
But experiments proved it.
Yes, experiments at the Stanford Linear Accelerator Center, SLAC, in 1968, effectively saw these point-like quarks inside protons, confirming the model. That was huge.
Okay, so quarks were established. What about the forces?
In parallel, theorists were working on unifying the forces. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg managed to unify electromagnetism and the weak nuclear force into a single electroweak theory.
Like Maxwell unified electricity and magnetism.
Exactly. A similar kind of unification. Their theory predicted the existence of the W and Z bosons as carriers of the weak force, and also required the existence of the Higgs field to give these carriers mass while keeping the photon massless. This was spectacularly confirmed in 1983 when the W and Z bosons were discovered at CERN, with masses exactly as predicted by the theory, a Nobel Prize-winning triumph.
Wow. What about the strong force?
The theory for the strong force, called quantum chromodynamics, or QCD, was developed in the 1970s. It describes how quarks interact via the exchange of gluons, carrying a property called color charge. Nothing to do with visual color.
Okay.
So by the late 70s, early 80s, most of the pieces were in place. The quarks, the leptons, the electroweak theory, QCD, the third-generation quarks and leptons were discovered over time, culminating with the top quark discovery at Fermilab in 1995.
Leaving just one missing piece.
The Higgs boson. The cornerstone needed to explain mass within the electroweak theory. The hunt for the Higgs took decades and massive experimental effort, finally culminating in its discovery at CERN's Large Hadron Collider in 2012. That discovery really solidified the Standard Model.
An amazing story of theory guiding experiments and experiment confirming theory.
It truly is. And the Standard Model, incorporating quantum mechanics, special relativity, and these sophisticated gauge symmetries like SU3, SU2, SU1, has been tested to incredible precision. It's arguably the most successful scientific theory ever developed in terms of its predictive power within its domain.
You mentioned the Higgs field giving mass. How does that work conceptually?
The idea is that the Higgs field fills all of space, even seemingly empty vacuum. As fundamental particles move through this field, they interact with it. Particles that interact strongly feel a kind of drag or resistance, which manifests as inertia that's mass. Particles that don't interact, like the photon, remain massless. The Higgs boson itself is an excitation, a ripple in this field.
Like walking through treacle, some feel it more than others.
That's a decent analogy, yeah. And the theory is incredibly predictive. It didn't just predict the existence of the WZ and Higgs, but also relationships between their masses and how they should decay, which have been verified.
And those 3 generations of particles?
They seem to be identical copies in terms of how they interact with the forces. They just have different masses, with each generation heavier than the last. Why there are exactly 3 generations is actually one of the big mysteries the Standard Model doesn't explain.
Ah, okay. And quarks have fractional charges.
Yes, plus 23 or negative 13 of the electron's charge, which is why protons, up, up, down, have plus 1 charge, and neutrons, up, down, down, have 0 charge. Leptons have integer charge, like the electrons minus 1, or are neutral neutrinos.
There's also this fascinating deep fact you mentioned in the notes about anomaly cancellation.
Ah, yes. That's a very subtle mathematical consistency requirement. For the Standard Model to be mathematically sound, specifically for its quantum corrections not to blow up, certain potentially problematic terms called anomalies must exactly cancel out. Remarkably, this cancellation only happens if the quarks and leptons are paired up exactly as they are within each generation. It's a beautiful internal consistency check that hints at a deeper structure.
So the math itself demands this specific arrangement.
In a way, yes. And the Higgs boson's measured mass, around 125 billion electron volts, GeV, fits perfectly with the expected decay patterns, further cementing its role in the model.
So its significance, it's our best map of the particle world.
Absolutely. It's one of science's greatest achievements, providing the framework for understanding what the universe is made of and how it interacts at the smallest scales we can probe. It guides all modern high-energy physics experiments at places like CERN and Fermilab. Scientists are constantly testing its predictions and searching for deviations that might point to new physics beyond it.
Any direct applications?
More than you might think. PET scans, positron emission tomography, in medicine rely on positrons, the antimatter counterpart of the electron, which is a fundamental lepton in the model. The production of medical isotopes often uses particle beams based on this physics.
Solar physics.
Our detailed understanding of how the sun produces energy through nuclear fusion relies heavily on the weak force part of the Standard Model, beta decay, neutrino interactions. Detecting solar neutrinos confirm these theories.
Cosmology links.
Yes, the Standard Model incorporates a phenomenon called CP violation, a slight asymmetry between how matter and antimatter behave. While the amount in the Standard Model isn't enough to explain why the universe is dominated by matter, it's a crucial part of the puzzle.
But you mentioned it's incomplete.
Critically so. That's why it's often called the theory of almost everything. Its biggest omission is gravity. It just doesn't include it. It also offers no explanation for dark matter, which we know makes up most of the matter in the universe, or dark energy, which drives cosmic acceleration. These are huge gaps.
And those parameters.
Right. It has about 19 free parameters. Things like the masses of the particles, the strengths of the forces whose values have to be put in by hand from experimental measurements.
Right.
A truly fundamental theory would ideally predict these values. Why these specific masses? Why 3 generations? The Standard Model is silent on these questions.
So its incompleteness drives future research.
Exactly. The search for physics beyond the Standard Model is one of the biggest drivers in particle physics today. But we shouldn't downplay its success. It explains why atoms hold together, strong force gluing the nucleus, EM force holding electrons, why nuclear reactions release energy, how particles get mass via the Higgs. It's a monumental triumph of reductionist science, showing that the incredible variety of stuff in the universe arises from just a few fundamental ingredients and interactions.
So this model reveals the fundamental alphabet of reality, the tiny particles that make up literally everything around you, including you. It's an incredible achievement, a real testament to decades of work. But the fact that it's still incomplete, that it doesn't explain gravity or dark matter or why the particles have the masses they do, well, that just shows us how much more there is to discover at the very edge of human knowledge. It's a profound understanding, but clearly not the final word.
Precisely. The quest continues.
All right, from the incredibly small world of fundamental particles, let's zoom out, way out to the grandest scale imaginable, the entire universe. This brings us to cosmology, the scientific study of the universe as a whole. We're talking its origin, its structure, how it has evolved over billions of years, and even its ultimate fate.
The biggest picture possible.
Exactly. And the cornerstone, the anchor of modern cosmology, is undoubtedly the Big Bang Theory. This isn't just an idea, it's a well-tested scientific theory. It states that our universe began approximately 13.8 billion years ago from an extremely hot, incredibly dense initial state. It wasn't an explosion in space, but rather an expansion of space itself, which has been ongoing ever since.
Carrying galaxies along with it as space stretches.
Right. And as the universe expanded, it cooled. This cooling allowed energy to condense into matter, first fundamental particles, then atoms, and eventually, under the influence of gravity, these clumped together to form the vast structures we see today: galaxies, stars, planets.
From a hot, dense soup to the structured cosmos.
And we have some incredibly strong evidence supporting the Big Bang. It's not just speculation. First, there's the expansion of the universe. Edwin Hubble discovered in the 1920s that galaxies are moving away from us, and the farther away they are, the faster they recede. This is exactly what you'd expect if space itself is expanding.
Hubble's law, a key piece of evidence.
Second, and maybe the most powerful evidence, is the cosmic microwave background, CMB radiation. This is this faint, almost perfectly uniform glow of microwaves coming from every direction in space. It's interpreted as the residual heat, the afterglow, from the very hot early universe, now cooled down by 13.8 billion years of expansion to just 2.73 degrees above absolute zero.
A fossil relic of the early universe. Its discovery was huge.
And third, the theory correctly predicts the abundances of the light elements hydrogen, helium, lithium that were forged in the first few minutes after the Big Bang, when the universe was a nuclear furnace. The amounts we observe today match the Big Bang predictions remarkably well.
Big Bang nucleosynthesis, another major predictive success.
But the story gets stranger in recent decades. Cosmologists realize that the stuff we can see, stars, galaxies, gas, dust, only makes up a tiny fraction of the universe's total content. The rest is made of two mysterious components: dark matter and dark energy.
The dark side of the universe which dominates.
Exactly. Dark matter is thought to make up about 27% of the universe's mass energy budget. It's invisible, it doesn't emit, absorb, or reflect light. We only know it's there because of its gravitational effects.
We see its gravity, but not the matter itself.
Right. Evidence includes galaxy rotation curves. Stars in the outer parts of galaxies orbit way too fast if only visible matter were present. There must be a lot of unseen mass providing extra gravity. Also, gravitational lensing, the bending of light from distant objects by gravity, is much stronger than visible matter alone can account for. Dark matter seems to form vast halos around galaxies.
A gravitational scaffold for structure formation.
And even more mysterious is dark energy. This makes up the largest chunk, about 68% of the universe's content. And its effect is bizarre. It seems to be causing the expansion of the universe to accelerate. It acts like a kind of repulsive force, or perhaps an intrinsic energy of empty space itself, pushing everything apart faster and faster.
Counteracting gravity on cosmic scales. A huge puzzle.
So, the modern picture of the universe's composition is pretty humbling. About 5% ordinary matter, the stuff we're made of, 27% dark matter, and 68% dark energy. A major goal of cosmology now is to figure out what these dark components actually are and to map out the universe's expansion history in detail. The timeline of the universe image in our sources gives a great visual overview of this grand cosmic story.
The history of discovering this picture is fascinating too. The idea of an expanding universe really gained traction with Georges Lemaître, a Belgian priest and physicist, in 1927. He proposed that the galactic recession Hubble later confirmed was due to the expansion of space itself, tracing it back to a primeval atom.
The seed of the Big Bang idea.
Exactly. The name Big Bang was actually coined somewhat derisively by Fred Hoyle, who favored a competing steady-state theory, but the name stuck as evidence mounted.
And the CM.
George Gamow and his collaborators predicted this leftover radiation in the 1940s based on the idea of a hot, dense, early state. But it was discovered completely by accident in 1965 by Arnaud Penzias and Robert Wilson at Bell Labs. They were trying to eliminate noise in a microwave antenna and found this persistent hiss coming from all directions.
Serendipity in science.
A classic case. Its discovery was the nail in the coffin for the steady-state theory and cemented the Big Bang model. Over time, this led to the development of the standard cosmological model known as lambda CDM. Lambda represents dark energy, often modeled as Einstein's cosmological constant, and CBM stands for cold dark matter.
Cold meaning?
Meaning the dark matter particles were moving relatively slowly in the early universe, which helps them clump together effectively to form the seeds of galaxies.
Okay. And the history of dark matter and dark energy discovery.
Evidence for dark matter goes way back to Fritz Zwicky in the 1930s, who noticed galaxies in the Coma cluster were moving too fast to be held together by visible matter alone. But it really took off in the 1970s with Vera Rubin and Kent Ford's detailed studies of galaxy rotation curves, providing undeniable evidence for unseen mass halos. Dark energy's story is even more dramatic. Einstein introduced his cosmological constant lambda in 1917 to force his equations to allow a static universe, which was the prevailing view then. When the universe was found to be expanding, he supposedly called it his biggest blunder.
But it came back.
Ironically, yes. In 1998, two independent teams studying distant type Ia supernovae, which are used as standard candles to measure cosmic distances, found they were dimmer and thus farther away than expected. This implied the universe's expansion hasn't been slowing down due to gravity as everyone thought. It's actually speeding up.
Wow, a huge surprise.
A Nobel Prize-winning surprise. The best explanation was some form of dark energy with repulsive gravity, behaving very much like Einstein's lambda. Subsequent precision measurements of the CMB by satellites like WMAP and Planck, combined with large galaxy surveys, have pinned down those percentages 5% ordinary, 27% dark matter, 68% dark energy, and confirmed the universe's geometry is flat.
And inflation.
That's another key piece. Proposed by Alan Guth in 1981, inflation is a hypothesized period of extremely rapid exponential expansion in the first tiny fraction of a second, like 10 sub 35 subseconds, after the Big Bang. It elegantly solves several cosmological puzzles, like why the universe is so uniform on large scales and where the initial density fluctuations came from that eventually grew into galaxies. These fluctuations are seen imprinted on the CMB.
So mathematically, it all hangs together using general relativity.
Primarily, yes. The Friedmann equations, derived from GR, are the master equations describing the universe's expansion rate, represented by the scale factor AT. They relate the expansion to the density of matter, radiation, and dark energy. Matter and radiation tend to slow down the expansion due to gravity, while dark energy, with its negative pressure, speeds it up.
And Hubble's law, VHOHE, is a direct consequence.
Yes, it describes the expansion we see today, where HA is the Hubble constant, measuring the current expansion rate around 70 kilometers per megaparsec.
What about the early universe physics?
Big Bang nucleosynthesis, BBN calculations are a triumph. Using known nuclear physics, we can calculate the expected ratios of light elements, hydrogen, helium, lithium, deuterium, formed in the first few minutes when the universe was around 1 billion degrees Kelvin. These calculations match the observed primordial abundances incredibly well.
And the CMB formation.
That happened around 380,000 years after the Big Bang. The universe had cooled enough, to about 3,000 K, for electrons and protons to combine and form neutral hydrogen atoms. This event, called recombination, suddenly made the universe transparent to light. The photons that were bouncing around could now travel freely, and that's the light we see today as the CMB, stretched to microwave wavelengths by cosmic expansion. Its spectrum is an almost perfect black body, confirming the hot, early universe picture.
And the tiny wiggles in the CMB temperature.
Those CMB fluctuations, just 1 part in 100,000, are incredibly important. They represent the tiny density variations present at the time of recombination, likely originating from quantum fluctuations during inflation. These denser spots provided the gravitational seeds around which matter later clumped to form galaxies and clusters. They are the ancestors of all cosmic structure.
How are dark matter and dark energy modeled?
Dark matter is typically modeled as a collisionless, non-interacting except via gravity fluid. Cold means it was non-relativistic early on, which helps it clump efficiently. Candidates abound: WIMPs, weakly interacting massive particles, axions, but none have been definitively detected yet. Its nature remains a huge mystery. Dark energy is often modeled simply as a constant energy density associated with the vacuum itself, Einstein's cosmological constant air, which is a constant negative pressure causing acceleration. If A stays constant, the universe will expand exponentially forever. Other models propose a dynamic field, quintessence, but A is the simplest fit to current data.
So cosmology tackles the biggest questions.
Absolutely. Where did we come from? What's the universe made of? What's its ultimate fate? The Big Bang Theory, coupled with Lambda CDM, provides our most coherent narrative of cosmic evolution so far. The CMB has become this amazing tool for precision cosmology, allowing us to measure the universe's age, 13.8 billion years, composition, and geometry with remarkable accuracy.
And it informs other fields.
Definitely astrophysics. Galaxy formation and the large-scale structure of the universe only makes sense if dark matter provides the underlying gravitational scaffolding. The nature of dark matter and dark energy are arguably the biggest unsolved problems in fundamental physics today.
What about the fate? You mentioned heat death.
If dark energy is truly a constant lambda, then the accelerated expansion will continue forever. Galaxies will recede from each other faster and faster, eventually disappearing beyond observation. The remaining stars will burn out, matter will decay or fall into black holes, which themselves will eventually evaporate. The universe would end up as a cold, dark, empty, maximum entropy state, the big freeze or heat death. Of course, if dark energy changes over time, other fates are possible, but this is the standard picture for now.
Depressing. Any links to particle physics?
Strong links. The very early universe was incredibly hot and dense, like a giant particle accelerator. Understanding that era requires input from particle physics, like the Standard Model, and likely physics beyond it. The puzzle of why there's more matter than antimatter likely involves particle physics processes that occurred fractions of a second after the Big Bang.
Limits to understanding.
Yes, the Big Bang Theory breaks down right at the very beginning at time zero, the singularity. To understand the Planck epoch, the first 10 sub 43 sub-seconds, we'd need a theory of quantum gravity that unites GR and quantum mechanics. That's the ultimate frontier. Culturally and philosophically, cosmology has had a massive impact. It overturned the idea of a static, eternal universe, replacing it with a dynamic, evolving one with a beginning. It raises profound questions about initial conditions, the nature of time, and our place in this vast, strange cosmos dominated by mysterious dark components. It's truly astonishing how much we've been able to piece together about the universe's entire history, from empirical data and the laws of physics.
So when you think about it, you are here because of the Big Bang. The atoms in your body, the carbon, the oxygen, the iron, were forged inside stars that lived and died billions of years ago, all unfolding according to these cosmic laws. Understanding cosmology isn't just about abstract concepts. It's about understanding your own cosmic origins, the incredible story of everything that led to you being here, and acknowledging the great mysteries like dark matter and dark energy that still lie ahead. It really puts our existence into a grand perspective.
It absolutely does, the grandest perspective imaginable.
Our journey through these big ideas now takes us to perhaps the most fundamental concepts of all, the very nature of space and time themselves. We often take them for granted, but physics has revealed that our intuitive understanding is, well, deeply flawed. This idea explores how our picture has evolved dramatically.
From a static background to an active participant?
Exactly. In classical physics, think Newton's space and time were considered absolute and entirely separate. Space was just this fixed, unchanging, three-dimensional stage where events happened. And time was like a universal clock, ticking away uniformly for everyone everywhere, independent of space or anything happening in it.
The common sense view, really, seemed obvious.
But then came special relativity. Einstein completely threw that out. He showed space and time are not separate, but are intimately interwoven into a single, four-dimensional entity called space-time. And measurements of space and time are relative. They depend on the observer's motion. We already talked about time dilation, moving clocks tick slower, and length contraction, moving objects shrink. Even the concept of simultaneity, whether two events happened at the same time, becomes relative.
No more universal now. It depends on how you're moving.
Then general relativity took it even further. It showed that space-time isn't just relative, it's dynamic. It's not a passive stage. It actively responds to the presence of mass and energy by curving. And this curvature is what we experience as gravity. So space and time aren't just the arena, they are players in the game.
Matter tells spacetime how to curve. Spacetime tells matter how to move.
Right. A direct consequence is gravitational time dilation. Time literally flows at different rates depending on the strength of gravity. Clocks run slightly faster up here than down at sea level because gravity is weaker higher up.
Measurably faster, with precise atomic clocks.
And a story might get even weirder. At the very smallest scales imaginable, the Planck length, around 10 sup 35 sup meters, and Planck time, 10 sup 44 sup seconds, physicists suspect that the smooth, continuous picture of space-time might break down completely. It might become a turbulent sea of quantum fluctuations, sometimes called quantum foam.
Spacetime itself might be quantized at that level. Grainy, not smooth.
And some theories of quantum gravity go even further, suggesting space and time might not be fundamental at all, but emergent. They might arise from a deeper underlying structure, perhaps related to quantum information or entanglement. Theories like loop quantum gravity propose space is built from discrete quantum loops or atoms of geometry. String theory requires extra spatial dimensions beyond our familiar three, curled up incredibly small.
So, the very fabric of reality could be radically different from our perception.
The big takeaway is, space and time are not the absolute, unchanging, continuous backdrop our intuition tells us they are. They are relative, dynamic, potentially quantized, and maybe even emergent.
It's been a dramatic evolution in thinking. Galileo introduced a limited relativity principle. Newton formalized absolute space and time, which worked incredibly well for centuries. But then came Maxwell's equations and the constant speed of light puzzle.
Setting the stage for Einstein.
Precisely. Einstein's 1905 special relativity was the first huge leap, forcing us to mix space and time via the Lorentz transformations to keep spans constant. Hermann Minkowski then beautifully articulated the four-dimensional space-time viewpoint in 1908 with that famous quote about space and time fading to shadows and only their union preserving reality. It showed the unity underlying the relativity.
And then GR in 1915.
The second massive paradigm shift. Space-time became dynamic, its geometry determined by mass and energy. This wasn't just theory. Lemaitre's work on the expanding universe showed that large-scale space itself is stretching over cosmic time.
So space isn't static.
Not at all. Then, in the latter half of the 20th century, came the challenge of quantizing gravity. John Wheeler, in the 50s and 60s, vividly imagined this Planck-scale quantum foam. Then came more concrete theoretical frameworks. Loop quantum gravity, LQG, developed from the 80s onwards by people like Ravelli and Smolin, proposed space is built from quantum states of the gravitational field spin networks, implying a discrete granular geometry.
Space made of chunks.
In a sense, yeah. String theory, which also emerged seriously in the 80s and 90s as a candidate for unifying everything, requires extra spatial dimensions, like 10 or 11 total, for mathematical consistency. These extra dimensions are thought to be compactified, curled up incredibly small.
Still trying to reconcile GR and QM.
That's the core challenge. There's also the problem of time. Time plays very different roles in GR, where it's a flexible coordinate, and standard QM, where it's a fixed background parameter. This leads to deep conceptual puzzles and ideas about time itself possibly being emergent.
Have we tested these ideas?
Many aspects of relativity, absolutely. Time dilation, atomic clocks, particle decay, gravitational time dilation, GPS, Pound-Rebka experiment, the relativity of simultaneity, accelerators, light bending, frame dragging, Graviprobe B confirms spacetime gets dragged around a rotating Earth, all confirmed. But the Planck-scale quantum structure of spacetime, that remains purely theoretical. It's far beyond our current experimental reach.
So mathematically, special relativity combines space and time into four vectors. And the key invariant quantity is the space-time interval. So that's called a Gabs four-round, which all observers agree on, even if they disagree on atoms separately. Lorentz transformations mix space and time coordinates between observers,
Reflecting the unified space-time structure.
In general relativity, the geometry is encoded in the metric tensor, subim-sub, which tells you how to measure distances and time intervals locally. Einstein's field equations link this metric to mass and energy. Different solutions describe different spacetimes, like the Schwarzschild metric for a black hole or the FLRW metric for an expanding universe.
Black holes are a particularly striking prediction, where spacetime is so warped that space and time coordinates essentially swap roles inside the event horizon, leading inevitably to a singularity in the classical theory.
And the quantum attempts.
Loop quantum gravity uses spin networks. A key prediction is that geometric quantities like area and volume are quantized. They come in discrete chunks at the Planck scale. This naturally avoids the infinities that plague other approaches to quantum gravity. Space emerges from these quantum states. Space-time emerges from their evolution, spin foams. String theory, on the other hand, posits that fundamental entities are vibrating strings. Consistency demands extra dimensions, perhaps curled up in complex shapes called Calabi-Yau manifolds. Different vibrations correspond to different particles, including the graviton. It hints at space and time being derived concepts.
And there are even more speculative ideas.
Yes, things like the holographic principle and the related ADA-CFT correspondence suggest that the theory of quantum gravity in a certain volume of space might be equivalent to a simpler, non-gravitational quantum theory living on the boundary of that space. This hints that space-time might be like a hologram, emergent from information encoded elsewhere. Deeply strange but mathematically powerful ideas.
Okay, significance and applications. GPS we covered.
Absolutely critical there. Particle accelerators need SR constantly. Astrophysics relies heavily on GR for understanding everything from binary pulsars and neutron stars to black hole dynamics and gravitational lensing. The Event Horizon Telescope interpreting that black hole image needed GR at every step to trace light paths in extreme gravity.
Future impact from quantum gravity.
Direct applications are likely very far off given the energy scales. But conceptually, understanding quantum space-time could revolutionize everything. Could it allow for things like wormholes or manipulating space-time? Purely hypothetical now, but who knows. More realistically, it might solve fundamental puzzles like the Big Bang singularity or the nature of black hole interiors.
And the speed limit.
The universal speed of light c imposes fundamental limits on causality effects, cannot precede their causes faster than light allows.
So the main impact is the intellectual revolution.
I think so. We've learned that our intuitive grasp of space and time is just an approximation. They are relative, dynamic, unified, warped by matter, can ripple as waves and expand cosmically. Time is not absolute. Space is not Euclidean everywhere. It's a profound shift in perspective, showing how physics has continually forced us to revise our most basic assumptions about reality. In summary, the nature of space and time is transformed from Newton's fixed stage to Einstein's dynamic space-time fabric, and the quest now is to understand its underlying quantum nature, which might reveal it to be something even more subtle and emergent.
This deep dive really challenges our most fundamental intuitions about existence itself. It's not just abstract theory about distant galaxies or black holes. It's about the very structure of the arena where everything happens, affecting every moment of your life, from the precision of your phone's navigation using relativistic corrections to the fundamental flow of time itself. It makes you question what space and time really are.
Indeed. The deepest questions physics asks.
And that brings us to our final big idea, which is really the ultimate ambition, the holy grail of modern theoretical physics. The quest for a unified theory. This is the grand endeavor to combine all the fundamental forces and all the fundamental particles into a single, elegant, all-encompassing mathematical framework often called a theory of everything.
The ultimate unification.
Right now, as we've discussed, we have these two incredibly successful theories, but they are fundamentally incompatible. We have the standard model of particle physics, a quantum field theory that describes electromagnetism, the weak force and the strong force, and all the known elementary particles, with stunning accuracy. But it excludes gravity.
Okay.
And then we have general relativity, Einstein's beautiful classical theory describing gravity as the curvature of space-time. It works perfectly on large scales, but it's not a quantum theory.
Classical versus quantum, the fundamental conflict.
Exactly. When you try to apply the rules of quantum mechanics to general relativity, or try to incorporate gravity into the standard model framework, the math breaks down. You get nonsensical infinities, probabilities greater than 1, and it just doesn't work.
The theories clash at their intersection, especially at very high energies or small distances, like inside black holes or at the Big Bang.
So the primary goal of a unified theory is to reconcile quantum mechanics and general relativity to find a consistent theory of quantum gravity. But the ambition often goes further. Ideally, to unify all four fundamental forces, strong, weak, electromagnetic, and gravity, into a single theoretical structure, perhaps showing they are different manifestations of one underlying superforce that only becomes apparent at incredibly high energies.
A single description for everything fundamental. That's the dream.
What are the main contenders trying to achieve this?
Well, there are several approaches, but two main ones have dominated theoretical physics for decades. First, there's string theory.
Heard a lot about that one.
Right. It proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings, maybe loops or open strands, existing at the incredibly small Planck length scale, around 10 sub 33 sub-centimeters. The different ways these strings can vibrate correspond to the different fundamental particles we observe: electrons, quarks, photons, etc. It's like different notes played on a violin string correspond to different particles.
Okay, particles as vibrations.
And here's the really remarkable feature. Among the possible vibration modes, string theory naturally includes one that has exactly the properties expected for the graviton implants, the hypothetical quantum particle that carries the gravitational force.
So gravity is automatically included.
Yes, that's a major reason for its appeal. Gravity isn't tacked on and emerges naturally from the theory. However, for mathematical consistency, string theory requires the existence of extra spatial dimensions, typically 6 or 7 extra dimensions beyond our usual 3, making 10 or 11 spacetime dimensions in total. These are envisioned as being curled up or compactified at an incredibly tiny scale, so we don't perceive them directly.
Extra dimensions.
Wow. String theory also generally predicts supersymmetry, SUSY, a hypothesized symmetry relating the matter particles, fermions, and force carriers, bosons, suggesting every known particle has an unseen superpartner. It also suggests that all forces might unify in strength at very high energies.
Okay, that's string theory. What's the other main approach?
The other leading contender is loop quantum gravity, LQG. It takes a different philosophical approach. Instead of starting with particles and trying to get gravity, LQG focuses on quantizing spacetime itself, applying the principles of quantum mechanics directly to the geometry described by general relativity.
Quantizing space and time directly.
Exactly.
Yeah.
LQG doesn't inherently unify the other forces with gravity, but it aims specifically for a consistent quantum theory of gravity. Its core idea is that spacetime geometry is not smooth, but has a discrete atomic structure at the Planck scale. The quantum states of the gravitational field are represented by structures called spin networks. A key prediction of LQG is that fundamental quantities like area and volume are quantized. They come in minimum possible chunks. This discreteness naturally avoids the infinities that plague other attempts to quantize gravity, like the singularity at the center of a black hole or the Big Bang.
So granular space-time.
That's the picture. There are also other ideas. Grand unified theories, GUTs, are less ambitious than a full theory of everything. They aim just to unify the strong, weak, and electromagnetic forces, the standard model forces, into a single force at extremely high energies, around 10 sub 16 sub GeV. They often predict proton decay and usually require supersymmetry to make the unification work neatly.
And supersymmetry is SUSY itself.
SUSY is more of a principle or framework that could be part of a larger theory. It proposes this deep symmetry between fermions and bosons, doubling the particle spectrum. If true, it could solve some theoretical problems, help the forces unify, and provide natural candidates for dark matter. The lightest superpartner particle is often stable,
So the ultimate vision is some single principle or equation.
from which all the known particles, all 4 forces, and the quantum nature of spacetime itself can be derived. A final, simple, elegant description of the fundamental laws of nature.
This quest isn't new, is it? Einstein tried.
Oh yes. After completing general relativity, Einstein spent the last 30 years of his life searching for a unified field theory, trying mainly to unite gravity and electromagnetism using classical physics, sometimes exploring ideas like extra dimensions, Kaluza-Klein theory. But these efforts failed, partly because the weak and strong forces weren't yet fully understood, and crucially because he resisted incorporating quantum mechanics.
Then came grand unification ideas.
Right. After the success of electroweak unification in the 60s and 70s, theorists like Georgi and Glashow proposed the first GUTs, like the SU5 model, in 1974, suggesting the standard model forces merge at very high energy.
Is there evidence for GUTs?
The main hint is that the measured strengths, coupling constants, of the 3 standard model forces, while very different at everyday energies, change with energy in a way that suggests they might converge to a single value at a very high energy scale. With supersymmetry included, this convergence appears much more precise in many models.
But proton decay hasn't been seen.
That's the main challenge. Most GUTs predict protons should eventually decay, albeit very slowly. Experiments like Super Kamiokande in Japan have searched for this decay for decades and haven't found it, setting incredibly stringent limits on the proton lifetime, well over 10 sub 34 sub years. This rules out the simplest GUT models, though more complex ones are still possible.
And string theory's history.
It actually started in the late 1960s as an attempt to describe the strong force holding quarks together. It didn't quite work for that, but in the 1970s, people realized one of its vibration modes perfectly matched the properties of the graviton, so it was repurposed as a potential theory of quantum gravity and unification. It went through ups and downs, but a first superstring revolution happened in the mid-1980s, when consistency requirements were better understood, leading to 5 apparently consistent versions of superstring theory in 10 dimensions. Then came the second superstring revolution around 1995, when Edward Witten and others presented evidence that these 5 theories, plus another 11-dimensional theory, were all just different aspects or limits of a single underlying, still mysterious framework dubbed M-theory.
Sounds very complex.
It is. But despite its mathematical elegance and promise, string theory faces major challenges. The biggest is the lack of direct experimental verification. Its predictions typically occur at the Planck energy scale, vastly beyond current accelerators. Critics also point to the landscape problem. The theory seems to allow a huge number, maybe 10 sub 500 sub or more, of possible vacuum states, making it hard to extract unique, testable predictions for our specific universe.
What about LQG's development?
LQG developed more steadily from the late 80s and 90s, focusing specifically on a mathematically rigorous, background-independent quantization of GR. It has had successes in describing quantum spacetime and resolving classical singularities, like the Big Bang potentially becoming a big bounce. Its main challenge is incorporating the other forces and particles naturally and demonstrating that it correctly reproduces classical GR in the appropriate limit.
Have experiments like the LHC helped?
The LHC was hoped to find evidence for physics beyond the standard model, especially supersymmetry, which many theories predict should show up around the TV energy scale. Finding superpartners would have been a huge boost for SUI-Y, GUTs, and string theory. But so far, no definitive evidence for SUI-Y has been found, pushing the possible energy scale for new physics higher and leaving theorists to reconsider their models. The Planck scale, around 10 sub 19 sub dV, where quantum gravity effects are expected to be strong, remains far out of reach.
The math must be intense.
It's strainly. String theory involves sophisticated geometry and topology to handle the extra dimensions, often Calabi-Yau manifolds, advanced quantum field theory on the string world sheet, and concepts like supersymmetry and various dualities, like T-duality and S-duality, which relate seemingly different versions of the theory and hint at emergent properties. Loop quantum gravity uses techniques from quantum field theory but applied to the variables of general relativity, Ashtekar variables, leading to the mathematics of spin networks and spin foams representing quantum states of geometry. It predicts discrete spectra for area and volume operators. Grand unification relies on group theory, seeking a single larger symmetry group like SU5 or SO10 that contains the standard models SU3, ASU2, AU1 groups. The mathematics predicts relationships between particle charges and force strengths. All these approaches push the boundaries of known mathematics and often suggest the need for entirely new mathematical structures. It seems clear that a truly unified theory will likely require a radical rethinking of our fundamental concepts, perhaps with space, time, and matter emerging from something deeper, like quantum information or entanglement.
So why pursue this if it's so hard and far from experiment? What's the significance?
Well, primarily it's driven by the desire for conceptual completeness. Having two fundamental theories, QM and GR, that contradict each other is intellectually unsatisfying. Physicists strive for a single, consistent description of nature. There's also the hope of simplification, that a unified theory will be more elegant and have fewer arbitrary parameters than the standard model and GR combined.
Any potential spin-offs?
History suggests yes. The pursuit of fundamental physics often leads to unexpected technological or mathematical advances. Think GR leading to GPS, or quantum mechanics leading to semiconductors and lasers. While direct applications of quantum gravity are speculative, the mathematical tools developed might find uses elsewhere. String theory, for example, has already had a significant impact on pure mathematics.
What about answering existing mysteries?
That's a major hope. A unified theory could potentially explain the nature of dark matter, for example, via stable superpartners in Cesier string theory, maybe shed light on dark energy, explain why there are 3 generations of particles, derive the fundamental constants, and resolve the singularities in GR, giving us a complete picture of the Big Bang and black hole interiors.
Could it lead to manipulating gravity?
That enters the realm of science fiction for now wormholes, warp drives. While some solutions in GR allow these mathematically, they usually require exotic matter or energy we don't know exists. A quantum theory of gravity might change the picture, but it's pure speculation.
Any other contributions?
The cross-fertilization of ideas is important. Concepts from string theory, like the holographic principle, ADS-CFT correspondence, have surprisingly become useful tools for studying other complex systems, like the quark-gluon plasma created in heavy ion collisions, or certain problems in condensed matter physics. It provides unexpected connections.
And it drives experimental development.
Yes, the quest motivates building ever more sensitive detectors for gravitational waves, proton decay, dark matter searches, precision tests of fundamental constants. These often have broader applications. Fundamentally, though, it continues the historical trend of unification in physics. Newton unified celestial and terrestrial mechanics. Maxwell unified electricity, magnetism, and light. The Standard Model unified the electroweak force. A final unification of all four forces would be the ultimate expression of this deep scientific and philosophical drive to find unity and simplicity in nature's laws.
But we should be cautious.
Absolutely. Nature doesn't owe us a simple, unified theory. It's possible gravity remains stubbornly separate from the quantum forces, or that unification requires principles we haven't even dreamed of yet. The lack of experimental evidence beyond the Standard Model so far is a significant challenge.
Still, the impact, if achieved, would be immense.
Profoundly so. If string theory is right, realizing that all particles are just vibrations of strings would change our view of matter. If LQG is right, knowing space-time is fundamentally discrete would change our view of reality's fabric. He would likely provide the ultimate laws of nature, answering long-standing questions and potentially transforming technology and philosophy in ways we can't foresee. Though calling it a theory of everything is a bit hyperbolic, it would explain fundamental physics, not necessarily complex emergent phenomena like biology or consciousness. But in summary, while a fully verified unified theory remains elusive, the ongoing efforts represent humanity's deepest attempt to understand the fundamental operating system of the universe, completing the picture started centuries ago.
This quest really isn't just for physicists scribbling equations on blackboards. It feels like the ultimate human endeavor to understand the absolute deepest secrets of existence. It pushes the boundaries of our imagination, constantly asking if everything we perceive, all the particles, all the forces, maybe even space and time themselves, is just a different manifestation, a different vibration perhaps, of a single underlying fundamental reality.
That's the allure, the grand vision. What stands out to you listening about this idea of finding one single unified theory for absolutely everything fundamental in the cosmos? Hashtag Touch had your outro.
Wow. Okay, what an incredible journey that was. From, the seemingly simple laws of motion that govern how a ball rolls, all the way to the truly mind-bending realities of quantum foam, entanglement, maybe even extra dimensions. We've really seen how physics continuously reshapes our understanding of the universe.
It really does. And it constantly challenges our everyday intuitions, doesn't it?
Every single step of the way.
But what's also remarkable is the power, and I think the elegance of these big ideas, how they build upon each other, how even theories we know are incomplete, like the Standard Model, reveal such profound truths about reality and push us towards even deeper questions. There's a real beauty in seeing how incredibly diverse phenomena can be described, often with stunning accuracy, by just a few fundamental principles and mathematical laws.
Yeah, we've traced that incredible progression from the classical world of Newton through the relativistic revolution of Einstein that reshaped space and time, into the bizarre probabilistic realm of quantum mechanics, and now this ongoing quest for a final unification, all while grappling with the huge cosmic mysteries of dark matter and dark energy. Just a testament to that relentless human curiosity, that drive to understand why.
So maybe here's a final thought to leave you with. If the universe truly is governed by a single, elegant, unified theory, as many physicists hope and believe, what does that imply about the nature of reality itself? Does it mean that all the staggering complexity we see around us, stars, galaxies, planets, life, is ultimately just a vast, intricate symphony played out according to the rules of a single, perhaps simple, fundamental instrument? And could understanding that instrument be the key to unlocking all of nature's secrets?
That is definitely a lot to mull over. We really hope this deep dive into the big ideas of physics has given you, our listener, a kind of shortcut to feeling well-informed, maybe sparked your curiosity even further, and perhaps inspired you to look at the world around you from your phone to the stars with a renewed sense of wonder and maybe a few more questions.
Keep asking those questions.
Absolutely. Until next time on The Deep Dive, keep exploring, keep questioning, and keep diving deep.